Hello, my name is Aarno Pärssinen and I'm Professor of Radio Engineering at the University of Oulu, and my specialty is from radio systems down to RFICs and antennas, so looking at the system holistically from the early specifications down to the implementation aspects. And today I'm going to talk about the 6G radio challenge. How we should understand 6G. Is it something that is totally new? Everything that we couldn't make in 5G with its evolution? Next scheduled major milestone in 3GPP roadmap? Revolution in communications? Natural evolution of technologies towards the next generation of communications and sensing? Or is it a radio or system? And sorry to say, but I won't answer any of these questions, but you can then make your conclusions after this talk. And if you look at the industrial visions and targets, there are many of those nowadays. And one that I picked from Nokia that is specifically important for anything what we are doing is that we need still more capacity. And 6G must be designed to provide at minimum 20 times more wide area capability than 5G. And that's going to be one of the major challenges at different frequencies and on different occasions. And where we should start the research. This is a slide from the HEXA-X project, which was European flagship in 6G. And we have there all key items on the physical layer, including radio channel modeling, waveform and modulation, beamforming, and distributed MIMO on different items. And in addition to that, we had the major focus on enabling hardware technologies because they are so much in the core when the speed of the communication and bandwidth requirements are getting higher. And flexibility, hardware complexity, energy efficiency, and spectrum efficiency are all related directly to this hardware side, but it has also a lot of impact to the other things. So finding a synergy and co-optimization of the whole system is extremely important. Today I will be talking about devices, from devices to wireless systems. And in my scope, the device is actually not a handset or a mobile phone, it is a transistor. And wireless system where I'm going up to is roughly the wireless radio link, so we can have a connection between a larger device than a transistor to a network like base station. In this case, in the picture, you can see a small base station illustrated. And if we look at the very initial 6G radio requirements, and this slide is also from the HEXA-X project, we see that the first wave of 6G, the data rate requirements are in the range of 100 gigabit per second. That may mean actually that we need to communicate at 100 to 2 gigahertz range, but there is still a strict requirement of the radio link range to be more than 100 meters. And the typical devices could be device to infrastructure communications, mobile backhaul or front haul applications in this case. We have also long-term vision towards the terabit per second, and then we may need to go up to 300 gigahertz range or even above. And I will show at the end of the presentation some of the examples really on the feasibility side of this from electronics perspective. Then if you think about how we can achieve 1 terabit per second, we need some bandwidth. And this illustration is showing you actually 3 different data rates from 100 gigabit per second up to 1 terabit per second. And the different typical modulations don't matter if they are single carrier modulations or OFDM. Roughly the bandwidth requirements in the big scale are the same. But what we can see from the y-axis is that whatever we do, we need actually bandwidths from 10 to 20 gigahertz up to much, much higher. And this is already an important message, because can we find such a spectrum and where we can find it and what to do with it? So getting higher data rates means larger bandwidth, and thus higher radio frequencies. And that's why 6G research, especially initially, focused mostly in 100 to 300 gigahertz range, and also discussion on the feasibility of the MIMO in mostly line-of-sight connections. And these topics are still valid, although of course there is a lot of research ongoing also at lower frequencies and maybe a bit lower data rates in overall capacity. Then do we finally need a terabit per second? Not always, so we should use it only when there is an absolute need for it. And this is a slide from friends from Keysight, where there is calculated roughly if we would like to transmit a hologram image of a 3-inch 3D object with reasonable picture quality, color and 60 frames per second, that will take roughly 10 gigabit per second. If we translate to high resolution requirements for the 6 feet full human size image, then we are easily in the range of 4.3 terabit per second. So this means that basically there might be applications. Are we getting that in a high enough quality already in 6G? Maybe that's too much to ask, but still we can find that some of the dreams related to the 6G can involve very high data rates as well. Of course, optimization in compression and how to transfer the things may get a bit easier specification, but definitely 100 gigabit per second may not be enough for this sort of huge image distribution systems, for example. So what are the enablers for wireless era? And I think we know them pretty well already from the past. CMOS and other semiconductor technologies, laser-based optics, and of course information theory. And I will focus in my talk on the first part of this. If we want to have more data, we go to higher frequency. We try to consume less power, if only possible, at least on average per bit. And automatically it will to a certain extent lead us to the shorter range that will be analyzed from different angles in this presentation as well. One of the key trends we see from the famous power amplifier performance survey, where we can see from the different technologies that how much the output power is actually reducing as we go higher in the frequency. And we see that the 6G starts to be quite much in the corner of the transistor capability when we start to see very sharp decline of different technologies, that they start to run out of steam to provide any power. And this also means that we are approaching the Fmax, which is the maximum frequency where any transistor can deliver power for transmission. So we cannot go beyond that for sure. Choice of the semiconductor technology is of great importance. We have used CMOS technology in most of the applications, especially for the mobile handsets, already for several decades. And as we go higher in frequency, silicon germanium by CMOS as the silicon-based technology has also risen more attention recently. However, they are not the fastest transistor technologies, and we know that the 3 to 5 semiconductor technologies like indium phosphide can do basically much better. And based on the models we have developed for the radio performance for different technologies, I've simplified the link performance and thus the relative range between those at 200 gigahertz. And you can see that if I normalize silicon germanium as 1x, I can get only 1/3 of the range using CMOS. And on the other hand, with the indium phosphide, considered to be one of the best technologies at the moment, almost 6 times the same range. This was at 200 gigahertz, but now we need to look at also that compared to 28 gigahertz silicon germanium technology, we are still shorter in the range. So this is a major challenge for all of us, how to make radios above 100 gigahertz, even up to 300 gigahertz, and how to get decent performance for them using the best and most suitable technology, which is not only about the performance, it's also about the cost and feasibility to integrate it together with the digital transistors and digital signal processing. Another interesting factor is actually how things are scaling. And as we scale up in the frequency, we scale down in area. And here are in the realistic sizes actually antennas at 3 GHz, 30 GHz and 300 GHz. And as you see, I have needed to magnify the 300 GHz antenna, especially from that small dot to a larger one, to illustrate you really what is happening. So one antenna will be significantly smaller, and as we know from the theory, we can compensate the additional losses per antenna over the air communication by using the same antenna aperture, which means that with the number of antennas we can replace the losses per antenna then that are inherited from the so-called path loss. Actually, it's really coming from the antenna aperture. Then if you look at a bit how electronics is fitting inside one antenna. In the left side, we are having a 2-channel commercial chipset for base stations that has 2 channels, so it in essence is much smaller than the 3 GHz antenna at lower frequencies, and therefore can very nicely fit to the same platform. At 30 GHz, we see that the typical construction of 4 antennas per IC chip is possible. And in this case, we are having the support also for the dual polarization. So we can see that the one chip can fit under the 4 antenna elements, in this case at 30 GHz. If we then go to 300 GHz, and there is a chip that we made to test the antennas and to measure those, I will present that a bit later, then we have actually antenna that it in itself equal in the size as the whole area reserved for it. And where we can fit the electronics is one of the big questions we need to address. Quite a big change compared to the 30 GHz if we are going 1 decade up in the frequency, not just in the transistor technology, but also in form factor. So there are many mountains of radio hardware and RFIC to climb before we can say that we have done it. And if we look at the historical perspective, at 1 to 2 GHz frequency range, the feasibility was pretty much done on the 90s. Large-scale integration was ready early 2000. And 2010 and so on, we have focused on the maturity and detailed advances, making the systems at 1 to 2 GHz very complex. We can do the ICs, we can manage the complexity in a totally different range than we were able to do some 20 years before that. At lower millimeter wave range, what I'm meaning up to 100 GHz, the feasibility was done pretty much in early 2000 from the IC point of view. Large-scale integration, there was already systems integrated at 2010s, especially in the 60 GHz Wi-Fi. And we are seeing the maturity and advances in 2020s. With sub-terahertz, so meaning 100 to 300 GHz mostly in this case, we have studied the feasibility once again later. Large-scale integration, can we do it in even by the 2020s? That's still much of a research question. And how to predict what we can do in 2030s in terms of maturity and advances. We must understand that the 6G timeline is coming very soon compared to some of these technologies and advances to really make them commercial. And I'm speaking here still mature processes in integrated circuits, meaning silicon and most advanced 3 to 5 technologies that we are having and have had there already for quite some time. Then some case examples from our own research in 5G and 6G RFICs to show you a bit of a glimpse what kind of things we have addressed at millimeter wave region. First, low noise amplifier that we did using silicon germanium, so silicon-based technologies, at 2/3 of the Fmax. And for those who are not very familiar with the transistor design, it's typically said that you cannot do any amplifiers above half of the Fmax. On purpose we broke it. We see, is it possible and is it feasible to do things even at as high frequency as 300 gigahertz? We noticed, of course, that we need to pay some price for it, but we were able to do a nice low noise amplifier that was working at 300 gigahertz range pretty nicely with some more than 10 dB of gain, and proved that's still feasible even with the silicon side. We did also a phase shifter based on the vector modulator principle and with digital controls to the same frequency range. That was a first time publication also in that frequency range, showing the silicon feasibility and relatively nice constellation diagram also on the different possible phases to be picked from the system. One must say that this was much more complex and difficult than at 10 times lower frequency, but seemed to be still feasible with specific tricks we developed for it. In addition to that, we are now having the most recent publication for the sliding IF receiver that converts down the 300 GHz signal in 2 stages to baseband and IQ signals for the digital conversion. And this has been now tested successfully, and we are working in the lab for the next phase of this development to think things together and make them as a combined system as well. Antenna is of course an important part of the system as well. And for that reason we developed an on-chip antenna that is possible to combine with the lens, silicon-based lens, and tested it with an IC that contained either a power detector or the previously designed LNA with a power detector to see what kind of ranges and what kind of performances we can get, as well as we were able to slide the lens and on-chip antenna relative to each other. So we got also very good information on how the steering and how the possible things can happen in mobility space. That is typically the most difficult challenge for any lens and highly directive fixed antenna space. And we have several publications also on this, and something that is accepted now also to transactions on microethereum techniques. So that's something to go for then with the details. If we then compare what a university group can do at the lower frequencies, so this is our 28 gigahertz transceiver chip done in 45 nanometer RF SOI that contains 8 channels for the phased array, and actually a complex architecture where we can combine RF signal processing, we can combine different things in the IF side, and then also translate the signals down to the baseband. And this is the most complex chip I've been working in the university domain ever, with some good and interesting results for the future development as well. The idea was really that how we can flexibly configure a larger panel with these chips without going to the symmetric antenna array combination and long wiring between the chips, but really go from chip to chip and utilize some of the things that are benefiting that architecture, as well as opportunities to see how beam squint should be handled in this sort of architectures. So the research is continuing based on this idea forward. Of course, in 6G, the best technology for every component is an important thing. And one of the things globally recognizes heterogeneous integration and 3G packaging. So I just wanted to mention that aspect here, and recognizing that the packaging part will be a much bigger role also in the RF signal processing in the future, enabling us to combine ultra-scaled CMOS, RF CMOS and BiCMOS processes dedicated better for the RF performance, and 3 to 5 semiconductors in the most optimal way. We don't have yet a working solution that is fully scalable, that is easy to handle, but definitely one of the research directions we need to take towards 6G very seriously. So what, when and how? In 6G, the technology will not take us automatically forward. silicon technologies and 3 to 5 technologies need to be tailored. We need to look at also the architecture level. We need to understand also how the communication system is working. And we need a very highly multidisciplinary perspective for that, preferably hardware aware or even friendly, protocol design for 6G. And once we have the technology, I'm sure that the new use cases will come after the enablement with the hardware. So now we are doing with the research, and next with the products. In the timeline, we are far enough to productize all of these fancy things. So what's the vision towards the 6G? Entropy tends to increase from business to technology in this field. So we are having more and more complexity both in business and in technology. How to get adjusted? This is one of the major things for us engineers to solve. We need to take all out from the existing. We need to make it better and create something that is not so obvious. And then, of course, there is always a dream that we should try to make the RF to look ideal, so that it's a black box and then the rest of the system can operate easily around it. This time I must say that it's maybe too much to ask. So what will be 6G? We will have a very interesting path forward. In the first generation of the 6G standardization, in its advances, and even for a longer term with the technologies that we are discussing today. So thank you very much.